About recursion for CS 141. So recursion, well, a recursive algorithm is a description for a way to solve a problem that refers to itself. So the algorithm and the problem somehow refer to themselves. So we'll look at a few examples of how this actually works metaphorically before we get into any code. So, this is another way to break big problems into smaller problems. So if a problem is small, just solve it directly. Otherwise, if the problem's too big to solve directly, just break off a piece you can solve and then solve the remaining smaller part of the problem. Right, so we break a piece off and then we solve that piece directly, and then we say, okay, solve the remaining part of the problem, which now is smaller because we broke a piece off using this same approach. So we call this first part the base case. If we've got something that's just small enough to solve, we'll just go ahead and solve it. Right? There's no need to worry about recursion. Otherwise, if it's too big to solve directly, we'll break off a small piece you can solve, and then just solve the rest of the problem, which is now smaller, using this same process. We just keep doing this until we eventually hit a base case, and then we're done. So let's think about some metaphors for this. So first of all, what if we want to show everything that's in a folder? Well, show everything in the folder, and then if something's a folder, well, just do the same thing we just did on the subfolder. Right, so let's think about this. Here's the C drive. What's in the C drive? Well, C drive is a folder. What does it have in it? Well, it has a bunch of folders. Well, some of those folders are folders, which have in them 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 folders, which have folders, but also some files. So the base case would be the folder's empty, or something's just a file. I can't show it's inside this file because it's not a folder, it's just a file. Right? There's no other files or folders stuck inside there. Right, so this is kind of this general idea. Another way to think about this, you can think of it as kind of like a tree. So, the desktop is a folder, and it has folders inside it. Now, my computer's a folder, which has folders inside it. C drive's a folder, which has folders inside it, and so on. This is a recursive structure, which is amenable to using recursive algorithms to list everything inside it. And what's great about recursive structures is it doesn't really matter where you start. So we're sort of starting this here and saying, well, we're starting at desktop and everything else is kind of inside desktop. Well, what if we didn't start with desktop? What if we started with C? Is this a valid folder hierarchy? Yes, of course it is, right? Because C is a folder which has these folders inside it. And for example, MS Office is a folder which has these folders inside it, right? So it doesn't matter where you cut this structure off, it works. Let's do it again. Let's start at MS Office. This is a folder which has these folders in it. This is still a valid folder hierarchy. That's totally fine. So here's some pseudocode. I say it's pseudocode because it's not real code. It's just the general idea of how a function like this might work. Suppose we want to list all files that are in something that's either a folder or a file. Well, if folder or file is a file, then just print it, right? Because we're just listing everything that's in there. Well, if it's a file, well, I can't do anything else with that other than just print it. Now I'm done. Well, if it's not a file, what do we do? Well, that means it's a folder, so for each thing that's in folder or file, where thing itself is either a folder or a file, call the function again. What's the function going to do? Well, it's going to take whatever subfolder or file was in the original folder or file, do this again. Now that subfolder or file, if it's a file, print it. Otherwise, if it's a folder, do the same recursion. Right? So it would say this is the base case. If we're given a file, well, I can't recurse with a file. That's the base case. That's the simple problem. I know how to solve that. I'll just print it. Otherwise, what do I need to do? Well, for each thing that's in the folder or file, here's my recursive step. Well, now I'm going to recurse by calling that same function on it. And this is going to go, this will print out all the files that are in folder or file. It's not actually going to print the folders. We could add a print statement down here where, else that has been a folder, you could print it, I don't know, whatever you want to do. But we got the base case, we got the recursive step. This will get you to every single file that's inside any given folder. Suppose you want to find a word in a dictionary. Well, you can do this, first of all, I should back up. Back in the olden days, dictionaries, we didn't have dictionary.com because there was no internet, so we had to have these giant books that listed all the words in them alphabetically, and if you wanted to find a word, and figure out how to spell it or look up its definition, you would have to flip through the dictionary until you found it. And of course, the dictionary might have, 100,000 words in it. We're not going to flip through all 100,000 words. You're going to use the fact that it's alphabetized to your advantage. That's actually a recursive algorithm. Here's how it works. Well, if there's no words left in the dictionary, then your word must not be in it, so you're spelling it wrong, or it's a word that just doesn't have a dictionary definition. If that's not true, that's kind of a base case, what do? Well, take the dictionary and kind of split it in half. Find the word that's in the middle. So, flip to approximately the middle page, find the middle word on the middle page. If that's the word you're looking for, you're done. You found it. If it's not the word you're looking for, well, then the word you are looking for is either before or after it. So then repeat this process number one with either the first half of the dictionary or the second half of the dictionary. Now keep doing that until either you run out of words in the dictionary or eventually you land on the word that you're looking for. Okay, so let's think about this with pictures. So I went and found, an image of like a side view of a dictionary, this good old, shot of Webster's dictionary. I found this here. So it's got all the words in it. What do? Well, pick the word that's in the middle. So split this into two halves, pick the word that's in the middle. If that's the word you're looking for, you found it, great. If it's not the word you're looking for, is the word you're looking for alphabetically before or after that middle word? Well, let's suppose it's after. Okay, now take just the second half of the dictionary where your word is, split that in half again. Right, so if this middle word is your word, then you've found it and you're done. If it's not your word, maybe your word now is before. Okay, split it in half again. Now do the same thing. Split this in half, pick the middle word. Is this your word? If it's not your word, again, is it before or after? And repeat. We keep doing this, and because of the power of logarithms, eventually we either find the word or we decide that the word is just not in there because we've checked every possible place that that word could be. What's amazing about this, so think about this. Imagine you have a really big dictionary, 1,000,000 words, or about 1,000,000 words. Well, we know from our powers of 2 that 2 to the 10th is about 1,000. It's actually slightly more. It's 1K, which is 2 to the 10th, but it's about 1,000. 2 to the 20th, that's about 1,000,000. 2 to the 30th, that's about 1,000,000,000. So if you have about 1,000,000 words in your dictionary, how many times can you cut it in half until you run out of, until you get down to something of size 1 that you can't really cut? Well, it's about 20. It's not exactly 20. It might be 21 or 22 depending on your implementation. But it's going to be about 20. 20 cuts is a heck of a lot better than having to look through 1,000,000 words. So there's power of cutting things in half. This recursive algorithm, super efficient for this kind of thing. Okay, moving on. How long is a really long line? You're waiting in line. It's a really long line. Maybe you're waiting for tickets to your favorite band is performing. Maybe there's like yet another Star Wars movie that everybody waits in line for. I don't know. Maybe it's for the cafeteria. Who knows? You're in a really long line. You don't know how long the line is. You can't even see the front of the line, but you'd like to know how long the line is. Now, you don't want to jump out of line and, go try to count because then maybe people won't let you back into your spot in line. So what can you do? Well, I don't know how long the line is, so I'm going to ask the person in front of me, hey, how long's the line? Now, they don't know how long the line is either, so they're going to ask the person in front of them, who also doesn't know, and this is going to keep going until eventually you get to somebody who's first, and they're going to say, I'm first. The line is of size 1. And then that's going to propagate all the way back. So, this is the essence of a recursive algorithm. The simple case, the thing that we can solve, the base case, is if you're first, then the line is of length 1. There's one person in line and it's me. And if you're not first, well, you don't know how long the line is exactly, so you're just going to have to ask whoever's in front of you, and whatever they say, you're going to add 1 for yourself. Right? So we're making the problem smaller because every time we do this recursive step, the line is a little bit smaller because each person's like, well, I don't know, so I'll ask the person in front of me. Who doesn't know? Who asks the person in front of them? Each time you do that, the remaining number of people to be asked is smaller until you eventually get to the last person who has to say, well, it's of size 1. Okay, moving on. Another way to think about this. If you're first, the length of the line is 1. Otherwise, ask the person in front of you and add 1 for yourself. Here's a visualization of this. I Googled young people waiting in line. This is one of the stock images that came back. Got it from here. So, I don't know. I'm last. Or, I want to know how long the line is. I can't really see the beginning. So, I don't know. I'm going to ask the person in front of me, how long is the line? And whatever they say, I'm going to add 1 for me. Well, they don't know how long the line is either. So they're going to ask the person in front of them, how long is the line? They're going to add 1 for themselves. That's what they're going to tell this person. So this person doesn't know how long the line is. Ask the person in front of them. who also doesn't know, etc. Eventually get to the person who's first. Well, the size of the line is 1, which is going to propagate back here. They're going to add 1 together to 1, get 2, to here, and so on, until you eventually get back to the person that initiated this process, and they're going to have the answer. That's recursion. It's beautiful. Other possible uses of recursion, factorial in math. So 5 factorial, what's that? Well, it's 5 times 4 times 3 times 2 times 1. So that means that 4 factorial is 4 times 3 times 2 times 1, and 3 factorial, 3 times 2 times 1. Ha-ha! Look at that. It's recursive. Brilliant. So let's think about this. Which of these is the base case? Go ahead over to Google Classroom and answer that. I'll wait. Bum-ba-da-bum-ba-da-ba. Did you come up with E? If so, you're correct. This is the base case. We know it's the base case because there's no recursion in here, right? This is the base case. It says, well, the smallest thing we might need to solve is 1 factorial. That's just 1. I can't make the problem any smaller. This is as small as the problem gets, and the answer is 1. Which is a recursive step? Think about that. I won't be offended if you pause me and go answer it. Did you come up with basically everything else? Sort of a trick question. There's not one recursive step. There's many recursive steps. These are all the recursive step, right? Because 5 times 4 factorial. Well, that's a recursive step. Now 4 factorial is 4 times 3 factorial. This is a recursive step, and so on. This is the only one without a recursive step in it because that's the base case. So how do we implement recursion in Java? What's this going to take? What is the most important element to implementing recursion in Java? Go ahead and answer this. Did you come up with D? I hope so. E is not really a thing. Lambda R, the recursion operator, total distractor answer. There is no lambda R, the recursion operator. I completely made that up. These things here, nested for loops, a for loop that's in a while loop, a function with a loop. It's possible that a recursive function would have all of these things. It's not likely. This is a function with a loop. That's probably fine. These two are probably too complicated. But I'm not saying there's no possible recursive function that could have that. However, a function that calls itself, that's the key to recursion. Going back one slide, nope. There we go, back a slide. If we look at this, factorial is defined in terms of factorial until you get to the base case, right? So it's a function that will potentially call itself for the recursive step. That's what recursion does. That's what recursion is. Cool. So let's look at some very simple examples for Java code. Let's start with blast off. So we're counting down until we get to yell blast off because the rocket takes off. So we start with some number to count down with, say, I don't know, 5. So if the countdown's 0, you're going to yell blast off. If the countdown's not 0, yell the countdown, for example, 5! Then decrease the countdown by 1, so decrease it to 4, and then start over. Well, now we're at 4. Is the countdown 0? No, it's 4, so we'll do this again. Yell the countdown, 4! Then decrease the countdown by 1, redo number 1, and so on and so on and so on, till eventually somebody gets to 0 and gets to yell, blast off! Super cool stuff. So let's look at this in Java code. It's going to look like this. Right, so we're going to say, okay, countdown. Well, here's what we're counting down, n. So if n is 0, we're going to yell blast off, and that's it, we're done. N is 0, we yell blast off, we're done. Otherwise, we're going to yell out the number, whatever n is, and then we're going to say, okay, now do a countdown of n minus 1. Right, so here we're making the problem smaller. The problem was 5, now it's 4, then it'll be 3, 2, 1, until eventually somebody gets to 0 and yells blast off, and that's going to end the recursive chain. Right, and I went ahead and put this, online here on REPL, so we can go ahead and run this. It's basically the same code. Boom, we get to blast off. Now, a lot of you are probably looking at this and thinking, well, what if some Weisenheimer gives us, negative 10? What's going to happen? Well, it's going to print negative 10, negative 11, and so on. Yeah, that's fair. So we may want to put something like, well, if n is less than or equal to 0, just yell blast off. Or we could put an if here and say, well, if n is negative, go ahead and throw an exception or something like that. There's a lot of options for doing error checking. It is something to think about. So base case, recursive step. Boom. Unrelated to recursion, just purely for your entertainment, the final countdown from Europe, fantastic 80s band. This is on the final countdown. It's an awesome song. Let me just jump ahead a little bit to get, yeah, look at this. Look at the big hair. Where do we got the, look at the, wait, playing on the drums. Yeah, there we go. Oh my gosh, rocking the guitars, keyboards, light shows. Oh man. Oh man, the 80s were fantastic for terrible music. I love it. So I just threw that in because the blast-off example. Let's do another Java example with factorial. So everybody pretty much starts with factorial. It's kind of a boring example, but it's actually pretty easy to think about, and it fits recursion pretty well, even if you don't really end up implementing it with recursion all the time. So let's think about it. Factorial of 5, well, that's just 5 times factorial of 4, which is 4 times factorial of 3, and so on, down until factorial of 1 is just 1. So, to do this as a function, I'm leaving the public off here. I think it was word wrapping, but normally when you're doing static methods or functions, you're going to stick a public in there. Just as a note, I've left it off, and it's not necessary in all cases if you're not sure how or why. It's not an important detail. The key thing here is factorial. It takes an int. It's going to return an int. We need a base case and a recursive step. Let's start with that base case. Which of these is the best base case? Think about this carefully. You can go ahead and pause this if you'd like and kind of go work on this on Google Classroom. Come up with something. Hopefully you came up with A. If so, you're right. This is the best base case. So if n is less than or equal to 1, we're just going to return 1. So if the problem is small enough to just solve it outright, just give the answer that solves it outright. Don't bother with any recursion. And this is great because now, if we're doing legitimate factorial and we get down to 1, we return 1, life is good. But if it's the case that somebody gives us like -50, and factorial is not really defined for negative numbers, we'll just go ahead and return 1, which doesn't really make any sense. But then again, their input didn't make sense anyway, so like, what were they really expecting if they said factorial of -50? We could also do a check and throw an exception, doesn't really matter. Either way will basically work. So why do these other 3 not work? Well, this will stop the recursion, but it just returns n minus 1. So if I say factorial of 5, this will just return 4, right? Because n minus 1, when n is 5, is 4. But factorial of 5 is not 4. It's 5 times 4 times 3 times 2 times 1, and so on. So this is not going to work. This is not going to work because this isn't a base case. This is a recursive step because the function factorial is calling itself. That's the recursive step. That's not the base case that ends the recursion. Same thing down here. This is also a recursive step because now it's n times factorial of n minus 1. That might be a useful thing, but not as the base case. So now we've got the base case, but we still need to do the recursive step. Well, which of these is going to be the best recursive step? Go ahead and think about that, and then go ahead and give your answer online. Did you come up with C? If so, you're correct. So let's think about this. Whoop. No, hold on. Go back. Ah! Damn it. Yep, there we go. Good. Okay. Great. So this is not a recursive step because there's no recursion in here. It's just another thing that kind of looks like the base case. This is just checking, well, if it's n less than or equal to 1, return 1, otherwise return n. That's no good. This just means that factorial of 5 would just be 5, which is obviously not correct. Right? There's no recursive step in here. We're not calling the factorial function again. So this can't be the recursive step. This one also can't be the recursive step for the same reason. This is just saying that 5 factorial would be 5 times 4. Okay, that's part of it, but it's 5 times 4 times 3 times 2 times 1. We need some other stuff in here to make the rest of that happen. This is not going to work either. This works because we're saying n times, here's the recursive step, and note the recursive step makes the problem smaller. Right, so no matter what n we start with, as long as n is positive, each recursive call makes the new parameter a little bit smaller till eventually one of those gets down to 1, and then boom, the recursion is going to end. So this is correct. This isn't going to work because this is saying that factorial of n has to return factorial of n times factorial of n minus 1. Well, the problem here is this means 5 factorial is defined as 5 factorial times 4 factorial. Well, what is 5 factorial? Well, it's 5 factorial times 4 factorial, which is 5 factorial, boom. This doesn't make the problem smaller, so this is going to lead us into infinite recursion, which, in general, we do not want. So, putting it all together, here's our base case, along with this n less than or equal to 1 to make sure if we get nonsensical values, we at least don't go on forever with the recursion. And then here's our recursive step. I went ahead and put this on REPL. Here we are in REPL. We can go ahead and run this, and it should print 100. No, this is, oh dear. Oh yeah, there we go. That's if somebody gave us -8 because they're a Weisenheimer. Note it doesn't go on forever. What I really meant to do is have this be, I gotta be careful because if I change these once, it changes it again. So I changed that last, this is take 2 of the video, believe it or not. Yeah, there we go, 120. Boom. Isn't that great? So now we've got factorial. So that's the basics of recursion, and we are done. Thank you so much.